All right, everyone, and welcome to continuity. This is the main video for the continuity section. This is the big, bulky video, but don't worry, you are in good company. We've got the class. The class is here. It's ready. Oh, the class is walking out of the classroom. You guys are on your own for this one. The class is standing on the whiteboard. So I want to talk about continuity, okay? So continuity, we're going to talk about continuity first at a point, and then we'll extend it to some more other things. So continuity basically just means connected. If a function's continuous, then it basically just means connected. That's kind of like an intuitive description here. So like, if you think about my position in the video, unlike those old solitaire things, my position would be a continuous function. It's all connected. It's moving. It's seamless. It's continuous. It's connected. I'm saying connected 50 times. But if we look at this is no longer, my position is no longer a connected function because I'm down here and then I'm up here. There's no in between, right? I just jumped to the top of your screen. So that's kind of where we're going. That's the intuition. The class has settled back down, possibly. Let's get into some math. So we're going to start by giving you some, just kind of, again, some things to look for when you look at continuity. I'm going to give a couple graphs here, and I want you to look at these graphs and identify why or where they're not continuous. Here we have a line with a hole in it. Here we have a line with a jump in it. Here we have a line with a hole in it that's similar to before, but now there's also a point out here. Here we have the reciprocal squared function. All of these are functions that have discontinuities. And in fact, all of these are also functions with an infinite number of continuous points as well. All right, there's infinitely many places where these functions are continuous, but then there's a couple places where we have discontinuity. Here, discontinuity, it's not connected. There's a hole. The limit exists, right? The limit is the y value at that hole, but the function value itself doesn't exist, so it's not connected. It's not continuous. Here, the limit doesn't even exist at this point. The limit from the left is this y value down here. The limit from the right is this y value up here. This is not continuous. Here, the function value exists, the limit value exists, but it's still not continuous. It's not connected. The function value is different from the limit. We'll re-examine that. Here, this function's not connected. It's not continuous. The limit pops off to infinity. Function's not even defined. It's not connected. The piece on the left is never going to connect with the piece on the right. And here the function's just straight up not defined in the middle. It's continuous on both pieces, but it's not connected between. It's not even defined between. So these are all different things that we're going to talk about. We're going to look about in this section when we talk about continuity. So let's get into the official definition, which I have hinted at. We didn't do the formal definition for a limit. We mostly did limit laws and intuitive definitions. The limit laws can prove things, but we can't prove the proofs. We didn't prove the limit laws because we didn't prove using the definition of the limit. We're skipping that. That's 2.5. But we are going to do the formal definition of continuity. Okay? So a function f is continuous, and I'm always going to abbreviate continuous. It's much too long of a word. A function f is continuous at a point, at a point A, if we need three things to happen. We need the limit as x approaches a of that function to exist. We need the function value. At that point, function value at a, to exist as well. But we also need a third thing. All right, let's look at this example. The limit exists. the function value exists. Now, if this circle up here, if this circle were actually down here, then it'd be continuous. But the fact that the limit value and the function value, right? Limit value is this y value, function value is this y value. They're not the same. If they were, it'd be continuous. That's the third requirement. So these both have to exist and they have to be equal. The function value has to equal the limit. If the limit and the function are the same, then it's continuous at that point. And again, this is only at a single point. So maybe for our whole definition, right, it's continuous at a point. And in a future video, we'll talk about what it means to be continuous over an interval. Hint, it's similar to what you might think, continuous at every point in that interval. But there's some other things kind of as well. So again, all these examples of discontinuity fail something. Like these are all discontinuities. What do they fail? Here, the limit exists, but the function doesn't. Here, the limit doesn't exist. Here, the limit and the function both exist, but they're not equal. Here, neither the limit nor the function exists. Remember that we write that the limit equals infinity, but it doesn't actually exist. Let's do some examples and work on this using this definition. Example 1. Determine whether f is continuous at a. And I'm going to give you a couple different functions and a couple different a values. And we're going to talk about and look about continuity. Nice English, Jason. So we're going to start with, we have a lot to do with piecewise functions here. And remember, piecewise functions just say that depending on where you're in the domain, so we use this top piece if our input is less than or equal to 3, and we use the bottom piece if our input is bigger than 3. And specifically, we're curious, is this function continuous at 3? So graphically, we could look at this and we'll check our answer graphically, but let's do it without a graph first. See how good our calculus is. All right. So let's look at this one and say, okay, what are the 3 things for something to be continuous? Find the limit, find the function value. Do they both exist and are they the same? Then it's continuous. So to find the limit, the two-sided limit at 3 is a little tricky. The two-sided limit of 3, well, at 3, we have to look at the left limit and the right limit. And remember that if the one-sided limits are the same, then that's the two-sided limit. And that's how we find limits for a lot of piecewise functions. So first, let's look at the limit as x approaches 3 from the left of this function. And notice that if we're to the left of 3, we're always using that top piece. So from the left, this is the same as the limit as x approaches 3 from the left of that top piece. This is a polynomial. Negative x squared plus 4 is a quadratic, a specific equation, specific case of a polynomial. And we have learned that polynomials, well, polynomials are continuous is why this is true, but we haven't gotten there yet. We learned that the limit of a polynomial is just a function value at that point. So this is just going to be negative 3 squared plus 4. Negative 9 plus 4 is negative 5, I believe. So the limit from the left is negative 5. Well, let's look at the limit from the right. If the limit from the right is the same, then we know the two-sided limit. And we have to keep on going. If the limit from the right is different, then the limit doesn't exist, and we can immediately say, if the limit doesn't exist, then this function's not continuous here, and we'll be done. So limit from the right of this function, again, as we're bigger than 3, anytime we're bigger than 3, we're always going to be using that bottom piece. That's going to be the limit as x approaches 3 from the right of that bottom piece, 4x minus 8, Jason. And again, this is also a polynomial. This one's a line. You can just evaluate at 3, and we have from our properties in the previous sections, that's true. Plug in 3, you're going to get 12 minus 8. Uh-oh. I mean, it's kind of good news because it means we have less work. So the limit doesn't exist, right? Left limit is different from the right limit, right? So on the left, we're like down here, and from the right, we're like way up here. So the limit doesn't exist. They're not connected. The limit does not exist. So f is not continuous at 3. Again, we need these to be the same. Give a nice angry face. That's how one way that we can check whether something's continuous, and one way that something can fail at being continuous. To be continuous, the limit has to exist. Oh, we failed that. The function has to exist. We actually did have that. And the limit has to equal the function. Let's do another one. Part B. B as in broccoli. Barbecued broccoli. Has anyone barbecued broccoli? I have not. I've literally never barbecued in my life, but my family barbecues a lot. Let's do part B. F of x equals sine x over x for all x except for 0, because this function is not defined at 0. This is not defined at 0. That causes us to divide by 0. An indeterminate form is what it's called. It's because you get 0 divided by 0 if you try to plug that in. And everywhere else, which is literally only one place, we say this function is equal to 1. And I'm curious, is this continuous when x is equal to 0? So I'm writing a equals 0, but I'm also asking at x equals a. So if a is 0, this is asking, is the function continuous at x equals 0? Well, we have to look at the limit, we have to look at the function value, and see if they're the same. So the first thing we check, right, what's the limit? Well, in this case, we can evaluate the two-sided limit directly, because to the left of 0, we use this piece. Oops. That should be a 0 right here. Otherwise, it's not a function. Fails the vertical line test. To the left of 0, we use this piece. To the right of 0, we use this piece. So that we can actually evaluate the two-sided limit directly here, even though it's a piecewise function. And we have from the previous section that this limit equals 1. This was one of our limit results that was on that sheet. We'll prove it at the end of the class, at the end of the quarter, not the end of this class. At the end of the quarter, we'll prove why this is using something called L'Hopital's rule. So the limit exists. It exists. Hooray! I don't know how to draw a happy face. That looks evil. That looks evil. So the next thing we have to do is, does the function value exist? Well, this is a piecewise function. When x is equal to 0, what piece do we use? When our input is equal to 0, we use this piece. This function value is equal to 1. Huh. That exists too. Let's draw a happier. No, that looks weird. I don't know. I think it's the eyes. So all that's left, so it's getting worse. All that's left is to check whether the limit is equal to the function value. Well, yeah, they equal. All right, so the limit as x goes to 0 of f of x is equal to the function value at 0. They're both 1. So yes, it's continuous. Continuous at x equals 0. That's how we prove continuity. Continuity requires 3 things. We check those 3 things. Check, check, check. And it's continuous. Last thing for this example, before we make one real quick epilogue to this video, I don't know. one more function. F of x equals x squared minus 4 over x minus 2. And we're looking at the point when x equals 2. So hopefully you remember a little something about rational functions. This function's certainly not defined. Oh, I spoiled the answer. This function is not defined when x equals 2. So we could check the limit, and it turns out the limit will exist here. But we already know the function's not going to be defined by 2. When we plug in 2, we're going to get a divide by 0 error. That means there's either a removable discontinuity or a hole. Sorry, a removable discontinuity is a hole. Either a hole or a vertical asymptote. But either way, f of 2 does not exist. So it can't be continuous. The function can't be continuous if it doesn't even exist here. Limits can exist, but continuity can't be a thing if the function doesn't exist. And there we go. That's how we prove that one. We need all three things in order for success, which means we only need one thing to fail. Just like a lot of things in life. Let's not turn this into a depressing math video, though. All right, so let's look at the definition again and really connect this with one more thing that we talked about in the previous section. When we found limits for polynomials, we had this theorem for polynomials, right? That said the limit of a polynomial is just the function value. Well, if the limit of a polynomial is just the function value, then the limit has to exist, the function value has to exist, and they have to be equal. So all polynomials, by that property and combining with this definition, have to be continuous. So that's a little theorem. Polynomials, I don't know how to spell. Polynomials, still don't know how to spell. And rationals are continuous everywhere on their domains. And you might say, Jason, hold up. Rational functions are continuous everywhere on their domains? Jason, we just showed this rational function wasn't continuous. But remember that 2 is not in the domain of this rational function. In fact, 2 is literally the only point that is not in the domain of this rational function. And this rational function is continuous everywhere except 2. All right. One final example, and then we'll finish this long video again. This really should be the mega video for this section, although I haven't done the other ones yet, so who knows? But that's my plan anyway. Where is f of x equals to x plus 1 divided by x minus 5? Where is this function continuous? Well, this is a rational function. I'm going to call it a rat. Learning after, I don't know if I should make this joke, but I'm taking notes from my League of Legends teammates, calling things rats. It's a rational function. So rational functions are continuous everywhere on their domains. So what's the domain? Is everything except for 5. The set of all x such that x is not equal to 5. There's other ways of writing that. So it's continuous on this same interval. So I'm just writing the same answer in different ways. Interval notation, set builder notation, they mean the same thing. All right. It's rational. That's its domain. So it's continuous everywhere on its domain. And that's our answer. That's pretty much it. Hope you survived. If not, then I'm just talking to the wall. Your fellow student has not paid attention. She has left. She never takes notes. And she causes problems for me. So y'all are better than October is as a student. Have a great day. Bye-bye.